Hey folks, Morgan here. We're back and we're talking about vapor pressure today. Now, as this year progresses, we have the opportunity to start getting deeper and deeper into subjects. We're talking beyond just, basic definitions, and we're increasing our mathematical treatment of things. So what we're doing today, not exactly AP related, okay, but it is something that is good background for AP. It's definitely part of Chem Olympiad, and just something that I really think you need to be able to understand this for me to say that I've given you a decent class in chemistry. So, molecules are in a constant state of motion and escape. Sometimes blocking the leaving area can slow them down. So, let's imagine that we have a container here. It's full of water. And here is a very distorted, large view of the particles in the water molecules themselves. They are all moving around at different speeds, but they have the same average kinetic energy. It's the Boltzmann distribution, or the ice cream graph we talked about before. And every now and then, one of these will be an outlier. It'll have enough energy to escape the attraction of the hydrogen bonding, and it will leave. And we called that vapor pressure back in a previous chapter. Now, I'm going to take the same container, same volume of water, throw that in there, but I am going to put in a solute. I'm going to throw in some particles of something else. So, when this one wants to escape, it has to push aside that particle before it can get out, which means it takes more energy. And fewer of the particles are going to have the necessary energy to escape, meaning the vapor pressure is going to be lower. Okay? And this is governed by or predicted by what we call Raoult's law. The pressure of a substance, which we'll call A, vapor pressure, above the liquid, is equal to the mole fraction of A times the vapor pressure of A when it is pure, when it's not in a solution itself. Okay? So this would be pure A, and this would be a solution of something dissolved in A. So that term is the vapor pressure of pure substance A. This just mole fraction. And this is the partial pressure of A above that solution. Okay? Now, mathematically, we can graph this out. And what we're going to see is a graph here where we put the mole fraction of A down here. And we have pressure on that axis, and this goes up linearly. It's a linear expression. And this is the vapor pressure of A when it's pure. So if the mole fraction of A is 1, just like pure water, normal vapor pressure. But as I add solute to it, its vapor pressure decreases until I get to the point where actually all I have now is the solute. They've switched, okay? I don't have any water left, so it would not exert any vapor pressure. Now, this is exactly what we would think we should see if everything in the world behaved as it should. That is what we might almost refer to as an ideal solution. Now, in an ideal solution, all of the interactions between solute and solvent are the same. There's no net attractive force, no net repulsive force, And this is just something that ain't often going to happen, let's be honest. Now, if we have a mixture of heptane and hexane, that could happen, okay? Because there's no hydrogen bonding or anything else going on in there. But I don't know a whole lot of other examples. Most of the time, it does not behave this linearly, this beautifully. So what we're going to deal with most of the time will be the non-ideal solutions. In other words, they interact. Now, that interaction might be attractive and it might be repulsive. Water with alcohols is a very good example. CH3OH, methanol or wood alcohol, would be a really good example of that. Okay, so let's go on to our next page here and do a little bit of algebra. The vapor pressure above a solution is going to be equal to the vapor pressure of A and the vapor pressure of B added together. So if we have heptane and hexane, which is an ideal solution, all we have to do is add their two vapor pressures together. We'll call that P hex and P hept. Okay? Pretty straightforward idea. And that vapor pressure of A is equal to the mole fraction of A times the vapor pressure of pure A. So I just did that wrong. I am so sorry. Vapor pressure A. Okay. Now, that means P total here, P of the solution, would equal the mole fraction of hexane times the vapor pressure of hexane plus the mole fraction of heptane times the vapor pressure of pure heptane. Now these two mole fractions are going to add up to equal 1. So in our graph from before, do pressure here, we'll do mole fraction on this side. Now, I'm going to draw this line going up, and we can call that the vapor pressure of whatever A is, however you want to define it. And I'll do another one here. We'll call that the vapor pressure of B. Now, the total pressure is the sum of those two. All right. Now, I just happened to make this one lower and that one higher. It could be the other way. All right. This is if we have an ideal solution. Now, if they were not ideal, our pressure might be higher or lower, depending upon the types of interactions. If you have strong interactions between the particles, okay, then the vapor pressure is going to be lower. So let's try and do this. We're going to do two graphs down here. Okay, now, what if we have two things that attract each other? Okay, water and acetone. Now, first thing, pressure, mole fraction. I'd have one that goes up. I'd have one that goes down. And the total, if it was ideal. But it's not ideal. Turns out they attract each other. So when it's just 100% A or 100% B, the pressures are exactly as I think they should be. But as soon as I mix a little bit of them, they attract each other and the vapor pressures drop down. So what I really see is what happens on this dotted line. Lower pressure than anticipated because of the attractive forces. And the total pressure in there will be lower than anticipated, and it being the lowest when the mole fraction is 0.5 and 0.5. Now it's also possible to have one, okay, where ethanol and hexane are mixed. Okay? They do not have much miscibility. One's polar, one's nonpolar. So I might have this anticipated set of pressures, but in reality, when I put them together, they repel each other. And the vapor pressures go up because they're repelling each other. All right, this over here is called a negative deviation from Raoult's law. Then, of course, this one would be called a positive deviation from Raoult's law. All right. Now, I'm assuming that almost 100% of the time, no matter what the combination is, one of them has a higher vapor pressure than the other. Water and alcohol would always be the alcohol. So no matter what, the vapor will always be richer in the more volatile component because it evaporates more. Okay, folks, that's a nice little side tour of vapor pressure. Okay, and we're going to see some more applications of that in the next lecture. Thank you for tuning in. This is Morgan, signing off.